last time, because we will use the diffusive approach to start thinking about the meridional overturning circulation. Okay, so we try to understand how deep is the wind influence. So all these wind-driven gyre theories that we developed, but how deep do they reach? So how deep does the wind stress is felt by the ocean circulation? So we started to think about simple scaling analysis of the depth influence of the wind. So we started with the thermal wind equations, which are just this. Did a scale analysis, and using linear dystrophic vorticity equation, this one, we reached this scaling for the velocities. And combining these two, we got an H, so the depth of the wind-driven circulation, which looks like that, just with a simple approach, first simple approach. Okay. Using the thermodynamic equations, we applied the scaling, and so eventually we got to this formulation for the depth of the wind-driven circulation, okay, which, as you can see, is a function of the Ekman pumping velocity, which is proportional to the wind stress curve. So that makes sense. The stronger the wind stress curve, the deeper the region that is influenced by the wind stress, and is inversely proportional to the stratification. So the stronger the stratification, the more difficult it is for the momentum imparted by the wind stress to reach deeper layers. Okay, so then we try to make slightly more general scaling for the thermocline, which is the region where you would feel the wind stress. And so we developed this very simple way of thinking of a circulation in the ocean, which is actually what we will start doing today again. And so we have sinking water near the poles, where the air is cold and cools the water. So the water gets dense, sinks to the bottom, creates a pressure gradient, starts filling the whole interior, and then eventually there must be some diffusion that mixes this very cold water, makes it slightly warmer, and there is a rising motion of this less cold water towards the surface. And at some point there will be a balance between this upward movement and diffusion processes, and where it stops is where you would form the thermocline. So we did a simple kinematic model looking at this advective diffusive process. So you have a vertical velocity on the left hand side and a diffusion on the right hand side. And so by using that simple advective diffusive balance, you integrate that given those conditions, and you get a temperature with an E-folding scale of kappa over W, the vertical velocity. And that is the scale of the exponential decay is what we started calling delta, which would be the thickness of the thermocline. Okay. So it depends on the diffusivity and the vertical velocity, of course. And so we started thinking of the circulation in this sense. You have a gyre at the surface, the ocean is felt until a certain point. You have here cold water convecting, filling up the abyss, and then some homogeneous diffusion throughout the basin that diffuses all that cold water back to the surface. And at some point there is this advection diffusion balance where you form this thermocline, where the temperature or the density changes very rapidly, and so you have warm water at the top and cold water at the bottom, and a region where density changes very rapidly, and the thickness of that region is given by that simple scaling. Okay, but that scaling, if you put some typical numbers into that scaling doesn't look like reality, because that depth is too shallow if you use real values of diffusivity and real values of Ekman, of vertical velocities, not Ekman velocities. Okay, so we started thinking of a more complete balance, and so we introduced the Ekman velocity. So we started with the planetary geostrophic equations. So you have the momentum equations at the top, the buoyancy here, continuity, and the thermodynamic equation at the bottom. So you can again derive a diffusive scaling. So you remove all the wind forcing, and so the only possible driver of the circulation is diffusivity, that kappa. And so you're going to find a diffusive thermocline. So a thermocline that is only due to a balance between diffusivity and vertical velocity, just like we did before. So by removing the wind stress, you get to this set of equations. After the vertical derivative of the momentum equation, you use hydrostasy, and you get the thermal wind equations. Okay. So you have the thermal wind equations here, you have the linear vorticity balance. You get a scaling of this. The first one looks exactly like the first one that we derived, kappa over W. But now we have the vertical velocity. Okay? We have the vertical velocity here, because we started with the momentum equations. So so you have the scaling for the vertical velocity, the horizontal velocities. And now if you substitute, you get a delta, so a thickness that looks like this. Okay. And for the vertical velocity, a scaling that looks like this. You put some typical numbers just like the way we did before. Changing buoyancy 10 to the minus 2, 5,000 kilometers, the length scale of the jar, F, and a typical value for diffusivity. And you get a thickness of about 150 meters and a vertical velocity which is something like 10 to the minus 7. And again, this vertical velocity is too weak. This is now the Ekman vertical velocity, okay, the Ekman pumping. And that's far too small. Okay, the observations show that the Ekman velocity is 10 to the minus 6, 10 to the minus 5. If you instead use kappa 10 to the minus 5, which is too large, that gives you a delta of 700 meters, which is more like observations, but the vertical velocity is still too weak. Okay. So diffusion is not enough to explain the observed values. And so we derived an advective scale. Okay, so the equation of motion is, so we say, okay, then advection must be the dominant factor here, so we ignore diffusivity totally, and so the thermal wind balance and linear geostrophic equation is what we're left with, because we neglected the diffusivity. Scales, they look similar to before. Take the vertical velocity is that of the Ekman pumping, and the depth scale is now given by this d, okay, which you can rewrite this way if you prefer. And now d is a function of the magnitude of the wind stress because it's proportional to the Ekman pumping, okay, which makes sense, and is inversely proportional to the strength of the horizontal gradient in buoyancy or in temperature, so the differential heating. If you put reasonable numbers for the Ekman pumping, 10 to the minus 6 or 10 to the minus 5, and you substitute into that scaling d, you get an estimate for the depth of the thermocline, which looks much more like reality, okay? Something like 1,000, 1,500 meters or so. Okay, so what we learned from this is that we can use two scalings. One is the diffusive scaling and one is the advective scaling. Okay. So the wind influence is given by the scaling d, which is the depth to which the wind-driven circulation can penetrate into the ocean interior. Okay, so that's the depth of the thermocline, d, which is given by advective processes. So it's given by the Ekman pumping. The stronger the wind stress, the stronger the Ekman pumping, the stronger the let's say, pushing down the articles. So that's how far the Ekman pumping can reach. So that's given by the scaling d. So over the depth d, so from the surface down to d, we expect to see the wind-driven jars, where you have the effect of the wind stress curl and the Ekman pumping at the bottom of the jar. Okay. Below D lies the abyssal circulation, which is what we're going to talk about today, which is not wind-driven. In the first case, we will not consider mechanical forcing. And then D, the diffusive scaling, is a different scaling. So the diffusive scaling gives you the thickness of this thermocline. So it's the transition region between the two water masses. You remember the warm water at the top and the cold water at the bottom. They are diffused. So the cold water gets mixed by diffusivity and becomes warm water. And so that scaling, that advection diffusion scaling gives you the thickness of this region where diffusivity processes are important. The advective scaling gives you the penetration of the wind stress, so the depth D, and the diffusive process gives you the thickness of the region where diffusivity is important. So the thermocline can be very deep and very thick, or it could be very shallow and very thin, for example. Okay, it's two separate things. So D is the depth of the thermocline, and delta is the thickness of the thermocline, okay, which is schematically reproduced by this figure. Okay, so D tells you how strongly those isopycnals are tilted, and so between the surface, that green line, and the blue isopycnal, that D is where the ocean feels the wind stress. And then those two blue isopycnals are giving you the region where diffusivity is important. So the diffusive thermocline delta. So within that delta, diffusivity is important and waters are mixed between the cold water below those blue lines and the warm water above those blue lines. Okay, so what happens? So that's the depth of the wind influence and the which gives you the thermocline, and the thickness of the thermocline, how thick this transition area is. So we have these wind-driven circulations at the surface, and we have developed a few theories for that. And now we know with some simple scalings how deep these wind-driven circulations are. Now below those wind-driven circulations, there's something else, which is the abyssal circulation. And we know that below those wind-driven gyres, there is a meridional overturning circulation. So if you remember what we are, that simple schematic that I showed you before, you have some cold water close to the pole, becoming very dense, sinking to the bottom, and then because of a pressure gradient, filling up the abyss. And then we said there is a diffusion process that brings that cold water back to the surface, making it lighter. So all that water, all that circulation that is filling up the abyss is a first interpretation of the meridional overturning circulation. So now we're going to develop a very, very simple model of that meridional overturning circulation. Which happens mostly below the main thermocline, obviously. Okay. So we know there's a deep circulation since a long time because of measurements and blah blah blah. And what we do, we also use, of course, numerical models to try to understand this meridional overturning circulation, and we can put observations into these numerical models to try to make them reproduce more accurately, let's say, what the observations are. And so at the beginning we will just use diffusivity processes. Okay, so we will assume this meridional overturning circulation is something like a convective cell. So you have differential heating at the surface. Somewhere it's getting very cold, it sinks to the bottom, and somewhere else there is very warm water and diffusive processes that brings the water back to the surface. So there is no mechanical forcing into this meridional overturning circulation. But now we know, and so that meridional overturning circulation used to be called thermohaline circulation, so driven by temperature and salinity differences, so density or buoyancy at the surface. But now we know that the wind stress actually plays a very, very strong role in this meridional overturning circulation. And so diffusion is actually not that important in bringing this water back to the surface. And if it was just diffusion bringing this water back to the surface, it would be a lot of across isopycnal transports, right? So diffusion of water, so crossing the isopycnals, becoming lighter and lighter, and getting back to the surface. Now we know, because of theory observations and models, that most of that water that sinks to the bottom flows towards the equator and across the equator all the way to the Southern Ocean, mostly adiabatically, along the isopycnals, not across the isopycnals. Some water crosses the isopycnals and gets diffused to the surface, but a large fraction of it flows along the isopycnals, so not much diffusion, and then goes back to the surface close to the Southern Ocean because of mechanical forcing. So close to the Southern Ocean you have a lot of Ekman upwelling, and all this water goes back to the surface because of the effect of the wind, not because of the effect of diffusion. So if you use numerical models, this is a numerical simulation that assimilates data. Okay, this is the North Atlantic. You have the North Pole at the right, 20, so this is the equator, and 20 south, so you're close to South Africa here, 30 south or something. Okay. So this is a numerical simulation that includes real data, so this is called data assimilation. Okay. And this is the circulation that you get. So the strange color there means clockwise, as you can see from the arrows, and the numbers are mass transports. So those are Sverdrups, 10 to the 6 meter cube per second. So you see a lot of water at the surface flowing towards the north, becoming very cold, sinking, and then recirculating back across the equator. Okay? You don't see many close circulation around the equator, so diffusivity here doesn't play much of a role. Most of the water crosses the equator and eventually will reach the Southern Ocean, where then it will go back to the surface through mechanical forcing. Okay, so this is the what we know about the meridional return circulation from a data simulating model. This is a ocean model solution again. This is the global meridional return circulation. So this is depth, latitude, and this is zonally integrated. Okay, so it gives you the whole transport zonally integrated across all longitudes. So you see a very large sinking near the North Pole, which is actually happening in the Atlantic Ocean, not in the Pacific. Okay? And then you see all those streamlines crossing the equator and going all the way to the Southern Ocean. So this is all adiabatic along isopycnals, and then all this water goes up to the surface through mechanical forcing. Okay, so this is all Ekman upwelling, and then it's recirculating towards the northern hemisphere. There is some close circulation here, so diffusion does play a little bit of a role, but most of it is circulating along the isopycnals. Okay. This is what we call the upper cell of the meridional return circulation, and then you see a anti-clockwise circulation. Okay, so this is negative, so it circulates the opposite way. And this is actually water formed near the Southern Ocean, where it gets very cold, but also very, very salty, much saltier than the one in the North Atlantic. So it's actually denser, and is able to sink all the way to the bottom. Instead, this one, as you can see, doesn't sink all the way to the bottom, because the bottom is filled with this very dense water, which is actually denser than the water formed in the North Atlantic. So this water formed near Antarctica is denser than this one formed in the North Atlantic. So this one flows below the North Atlantic upper cell. Okay. And then you see some other circulations here close to the surface, which are actually mechanically driven. Those are called subtropical cells. Those are totally wind-driven cells. Okay. But this is the circulation that we know from the models, and it looks quite realistic. And so we're going to try to understand how this works, but in the first place, without thinking about the wind-driven influence. So just the effect of the inferential heating of the surface. So very cold surface condition here, and very warm surface condition near the equator. Okay, so we will try with what is called a buoyancy-driven overturn. So simply driven by changes in buoyancy. And when you do that, you're actually developing what is called in fluid mechanics sideways convection. Okay, sideways because it's going to convect, let's say, from right and left. And you can get that sideways convection simply by heating or cooling at the surface from a non-uniform buoyancy profile. Okay, so here you're heating close to the equator, and here you're cooling close to the other edge of your box. So you have a differential heating at the surface, and so you will be heating on this side of the box and cooling on this side of the box. Okay, so if these are buoyancy lines or temperature lines, if you prefer, it will be very warm here close to the equator, and then it will get cooler and cooler until you reach this region where you actually have some net cooling at the surface. And here you will get some very cold water being formed, becoming very dense and actually sinking to the bottom. Okay, so this is the simplest way of starting to think about the meridional overturning circulation. Just sideways convection, totally buoyancy driven. Okay, so we're going to try to derive a solution for that, and then we'll see some numerical results. So you start with the Boussinesq equations of motion. These are the momentum equations. You have buoyancy, a viscosity parameter there, buoyancy equation, and continuity. The top boundary condition is the buoyancy forcing that you give at the surface, okay, which is some function f, doesn't matter, okay, which is a function of x, y is at the surface, and it could be a function of time. But the important thing is that you're heating on one side of the box and cooling on the other side of the box. We may think of this problem as a two-dimensional problem, just like the sketch that I showed you before. So just latitude and depth or height. Okay. And so you do a zonal average. Zonally average zonal flow is small because you've been integrating that zonally. And so you can use, the flow is going to be no divergent, and you can use the stream function definition for your meridional flow and vertical velocity vector. Okay, so you have this definition for the stream function. You take the curl of the Boussinesq equations of motion, the ones at the top, and you get to this. Okay, after taking the curl, you no-dimensionalize by choosing these no-dimensional parameters, and you plug those no-dimensional parameters into the equations. The important thing is the result. Okay, you put the no-dimensional variables into your equation, and you get this expression. Now you can make the choice of psi, the no-dimensional stream function, like this, because you have this, and you start substituting things into your equation. You rearrange a little bit your terms, and eventually you get these three nice parameters here at the bottom. Okay, this sigma, this alpha, and this number. Okay, so Ra is the Rayleigh number that I'm sure you remember from fluid dynamics, which measure the strength of the buoyancy term against the term of the diffusivity term. Okay. So if the Reynolds number is very large, it is buoyancy driven. If the Reynolds number is very small, diffusion wins against the buoyancy force. Okay. Sigma is the Prandtl number. Did you look at the Prandtl number in fluid dynamics? Yes? So sigma is the Prandtl number, so this nu over kappa. And alpha is an aspect ratio of the box, h over L. Okay, and h is the height of the box, and L is the length of the box. Okay, so after rearranging your no-dimensional momentum equation, look like this, and these three parameters appear: Reynolds number, Prandtl, and an aspect ratio for the box. Now, the important here is that we try to understand a steady solution, and so we make the assumption of steady and no turbulent flows, and statistically steady. And so what we try to set the first thing is that the buoyancy term, that Reynolds number, is on the order 1. Why do we want to make the buoyancy term on the order 1? Is that if the Reynolds number or the buoyancy term is much smaller, then buoyancy doesn't win against diffusivity and it's not a buoyancy driven overturning circulation. So it cannot be very small. If it is too large, it is not a steady solution because there's nothing to balance that very large term. So we make it on the order of 1. Okay, and that can only be true if the vertical scale h over L is set accordingly, and so we set also this sigma on the order of 1, and now we can make these assumptions. Alpha, that aspect ratio, which was alpha to the 5th, here at the top was alpha to the 5th, so alpha to the 5th, h over L to the 5th, if you rearrange, gives you this, and so h, the height of the box, looks something like this, which, if you use the expression for the Reynolds number and the Prandtl number, looks like this. Okay, so this is h. And the string function psi, you start rearranging things, and eventually you get an expression for the string function that looks like this. Okay, just rearranging terms. So these are the scaling for the height of this buoyancy-driven box and the strength of the circulation in a buoyancy-driven circulation. Okay, so buoyancy has to be on the order of 1, otherwise it's too small or it's too large. If it's on the order of 1, you take those no-dimensional parameters and you get an estimate for h and for the strength of the circulation that looks like this. Now we can do a numerical experiment of a buoyancy-driven circulation and see if these scalings are realistic. So here there is a couple of solutions. This is the density profile in our box, so this is height or depth, and this is latitude. And this is the string function psi in two different cases where the Reynolds number is relatively small and here the Reynolds number is relatively large. Okay, so what happens here is that first most of the box is filled with the densest available fluid, and the densest available fluid is given by the boundary condition at the top. That's the coldest or densest water that you can fill. There's not going to be any colder or densest water because it's given by the boundary condition. And most of the box is filled with that densest water available. Right? And there's a boundary layer in temperature near the surface, which is similar to the thermocline thickness that we derived. Okay? So this is all very dense or cold. Okay? And this is the, okay, so I should have said that this is the equator, so here is very warm, the boundary condition, here is very cold, and here is very cold. Okay, we're getting two symmetric circulations, not just one. So you have the very dense water at the bottom, which is eventually mixed through diffusion with the very warm water at the surface. And you have something like a thermocline here, which is relatively shallow. Okay. So most of the box is filled with this very dense water. And there is a boundary layer in temperature, which is our simple thermocline. Okay, this change. The boundary gets thinner with decrease in diffusivity. Okay. And decrease in diffusivity means large Reynolds number. Okay, so if diffusivity gets smaller, where is Reynolds? Here. If diffusivity gets smaller, Reynolds number gets large, and so for a large Reynolds number, this thickness, this thermocline gets thinner and thinner. Right? It makes sense. Diffusivity is small, so it cannot mix a lot into the interior. Okay, and this is a diffusive prototype of the oceanic thermocline. Okay. Second thing is that the horizontal scale of the overturning circulation is large. These cells that you see, the string function, these cells are very large. Okay? even in the large Reynolds number case. And the returning gets weaker with decreasing diffusivity. So again, large Reynolds number, which is the bottom case, the circulation gets weaker and weaker. And that's also given by the scaling here, psi, okay? With a small diffusivity, the circulation gets weaker, so that makes sense with our scaling. The downwelling regions, or the region of convection, where the water gets very cold and sinks to the bottom, is smaller than the upwelling region, okay? Especially as the Reynolds number increases. For realistic choices of the diffusivity, the convection is much more efficient than the diffusion, so it can happen in a small area. Convection is very efficient, sinks down in a plume and convects all that water, whereas diffusion is not so energetically efficient, so it has to work on a larger area. So convection will be relatively located in a small area, and diffusion process has to be in a large place. So this is what you get here. Okay? So this is where the convection and then the diffusion acts on a larger area, especially for large Reynolds number. Okay? So the scaling makes sense given the numerical results. A few points to remember after this simple scaling. No water can be denser than the densest water at the surface, of course, because if the surface water is denser than the water at depth, then it will be convectively unstable and sink in a plume. Okay, so you get very cold water at the surface, and that's the coldest water that you can form, is at the surface. The plume slowly entrains the warmer water that surrounds it and spreads horizontally, okay, after heating the bottom. Because when this cold or dense water reaches the bottom, then creates a horizontal pressure gradient and starts spreading into the interior of the box. And so the domain fills with the densest available fluid. Then this densest available fluid will be mixed by diffusion until a certain height, depending on the strength of the diffusivity. This process is a continuous one, because the plume takes cold water from the surface into the interior, where the water is then slowly warmed by diffusion, okay? And then the source of cold water at the surface is continuously replenished. So you have cold water sinking to the bottom, gets diffused, becomes warmer again. At the surface finds a boundary condition that is cooling the water, which sinks again. Okay? So if you have differential heating or a differential buoyancy at the surface, this will give you a continuous circulation. The value at the surface is given by the boundary condition, which is some function of the buoyancy at the surface. And so the interior cannot fill all the way to the surface because you will have a boundary condition at the top. And so there must be a boundary layer connecting this very cold water that is filling the abyss and the surface water that is given by the boundary condition. There will be a boundary layer, and the thickness of that boundary layer is given by that height scaling that we derived before. The larger the diffusivity, the thicker the boundary layer. Okay. And then finally, it is important to realize that even for large diffusion, so you might diffuse a lot the water, the interior, the abyss, okay? But there will never be a stationary solution as long as you have a differential buoyancy at the surface. You will be always generating dense water on one side of the basin and then diffuse that cold water back into warm water on the other side of the basin. So as soon as we impose a temperature gradient at the surface, or a buoyancy gradient, the top fluid begins to circulate. Okay? And basically that's because it's a baroclinic fluid. You have warm water on one side and cold water on the other side, and you start forming cold water, filling up the abyss, and then diffusion brings it back to the surface. So if you have a temperature gradient, it leads to a density gradient, and if you have a density gradient, you have a pressure gradient, and a pressure gradient leads to motion. Okay? So as long as you have a temperature gradient or a buoyancy gradient at the surface, there will always be a circulation. There will never be a stationary state. Okay? So waters that will fill the deep ocean can only return to the sea surface as a result of diapiconal eddy diffusion in this very simple sideways convection. The only thing that brings this cold water back to the surface is diffusion of buoyancy. Okay. So this is where Munch looked at this problem, and he came up for an estimate of a global average of diapiconal eddy diffusivity of 10 to the minus 4, given the amount of water that sinks to the northern latitudes and the amount of water that goes up to the surface. He said, okay, well, the amount of diffusivity that you need to bring all this cold water back to the surface is a global estimate of 10 to the minus 4. And so Munch assumed that most of the ocean is dominated by a balance between the vertical advection and vertical diffusion. Okay, this is the equation that we use to explain the thickness of the thermocline. So, given the amount of vertical velocity, the only value for eddy diffusivity that can explain or can bring all this cold water back to the surface is something like 10 to the minus 4. But the observed diapiconal eddy diffusivity in the open ocean is an order of magnitude smaller than 10 to the minus 4. Okay, so a global average or a typical value for eddy diffusivity in the interior of the ocean is actually 10 to the minus 5. It's not 10 to the minus 4. So diffusion alone cannot explain the going back to the surface of all this cold water, and that's why the observations actually see, we can see from observations that most of the water flows along the isopiconals all the way to the Southern Ocean, where it's brought back to the surface through mechanical forces, not diffusivity. And that's because diffusivity alone cannot bring all this water back to the surface, because you would require a diffusivity of 10 to the minus 4, which is not observed. Okay? The diffusivity is actually 10 to the minus 5. So sideways convection cannot be the only way of interpreting the meridional overturning circulation, because the observed values of diffusivity are not large enough to explain this warm water going all the way to the polar regions, cooling, filling up the abyss, and diffusion to close this meridional overturning cell. This diffusion process is not large enough in the real ocean. So there must be another way of bringing all this water back to the surface, which is actually mechanical force. Diffusion alone cannot do this. Okay, but a first interpretation of the meridional overturning circulation can be through diffusion processes. Even though we know that diffusion is not enough to explain the meridional overturning circulation, we know it now, but people didn't know it in the 60s, and so they developed this very nice toy model for the abyssal circulation, which takes into account diffusion only. Okay, and this is called the Stommel-Arons model. So Stommel again, basically Munch and Stommel were doing all the work back in the time. Okay. So what they did is they modeled the deep ocean as a single layer. Okay, so just one layer for the deep ocean. Above that deep ocean layer is the wind-driven circulation. And they imagine a localized injection of mass at high latitudes, so where the water gets very cold, injects mass, so sinks to the bottom, and brings mass to this bottom layer. And they call it S0, and that represents convection. How do you bring that mass back to the upper layer? Is through upwelling, okay, and through diffusive processes. And so the thickness of this bottom layer is a constant h. Okay, so there is a balance between the water that sinks to the bottom and the water that is upwelled to the surface. So you have a constant surface layer where the wind-driven jars are, and a constant bottom layer where you have the abyssal circulation. what they did, we're going to assume that this upwelling is nearly uniform. So you have a localized sinking, and then everywhere else you have upwelling through diffusion. The ocean is flat, and you have a western boundary current that that closes the loop in order to conserve mass. And basically we are looking at this case, okay? So you have a top layer where you have the wind-driven gyres, and you have a thermocline, and you have an abyss constant height h. Okay? So you have here localized sinking through convection, and then all this water all this mass that is injected into the bottom layer is upwelled through diffusion uniformly throughout the ocean. Okay, and here we set our equator. Okay. Then the water will have to go back to somewhere to the North Pole, and we'll see how it does it. So you take the Prandtl momentum equations again. They look like that. You eliminate the pressure terms, and you get the vorticity balance. Okay. So the vertical velocity W is given by this diffusive process, and is uniform because diffusivity is uniform throughout the domain. So vertical velocity is positive at the top. You have this vertical velocity bringing this mass back into the upper layer, and it's zero at the bottom. Okay. So this vorticity balance is beta v, so you have a meridional velocity, which is equal to this vertical velocity at the top, W naught, over h. Okay, so if the vertical velocity is positive because it's bringing mass up to the upper layer, then it means that if the vertical velocity is positive, then v, the meridional velocity, is also positive. So now I will try to build slowly the solution here. Okay, so we have a localized sinking near the northern latitudes, and then we have a uniform upwelling with a vertical velocity W naught, which is positive, and so we have a positive meridional velocity. Okay, so this is going to be my meridional velocity, which is positive. Now you know Justoffic balance. That gives you V1 over F, the pressure gradient. Okay, so let's do this. So the pressure gradient, so the pressure is given by psi. You integrate from, this is x e x m w or x whatever. So we integrate from x to xe. The meridional velocity, which is f over beta w naught over h over f, so that's f squared, and this is f squared h w naught from x to xe. Okay, so that's the pressure field. So we're assuming the boundary condition psi equals 0 at x equal x east. dy. So anyway, so you can get an expression for u now, which is again in geostrophic balance. You substitute, you get 1 over f d by dy of the pressure, which is f squared beta h w naught x minus xe, or xe minus x because I changed the sign, because there's a minus here, so I flip it, and that's 2 over h of w naught xe minus x. Okay, we do the d by dy of that. So given the geostrophic balance, we have a positive vertical velocity, and that gives me a positive meridional velocity. I know the expression for the meridional velocity and the zonal geostrophic velocities, and I can derive the expression for the pressure field. If I substitute, I get an expression for the zonal velocity. And then you might ask yourself, are we conserving mass with this simple model? You substitute into the continuity equation du by dx plus dd by dy, dw by dz. Then you have u, which is this expression, okay, plus d by dy, and v is simply f over beta w naught over h. Okay, so that's the second term, and the vertical velocity w naught over h. And that gives you twice w naught over h minus twice w naught over h, so we are conserving this, okay, which is the first important thing. So we have a positive meridional velocity and a positive horizontal velocity, okay? So this result is telling us that the zonal velocity is eastward, okay? It's towards the east. So we have a positive meridional velocity and we have an eastward horizontal component. So the solution is building this way. And you will see how we get to that. Okay, so this simple model gives me an expression for a vertical velocity that is providing a positive meridional component of the velocity and an eastward or positive zonal component of the velocity. So now we can play a more simple game of using just a sector ocean. Okay. And the sector ocean is going to look, well, I'm keeping that. This. So the sector ocean is going to look like this. So now we're looking at the ocean from the top. Okay. So we have the equator here at the bottom. Then we have x east, x west, and then y is the abscissa.
Over the east or in?
Sorry?
The xe over the e is an indication for east?
Yeah. I made a mistake doing the notes. That this I should have changed the notation. This should have been y and y north. So maybe this was confusing. But anyway, this side of the diagram and this side of the diagram, call it yn, y north. Doesn't matter. Once you integrate, doesn't matter. So now we're looking from the top. So we're looking from the top here of the ocean. And we have x west, x east, then y goes like this. And we have the pole at the top, and this is some latitude y, where we're going to do our budgets. Okay, so we have considered uniform upwelling velocity, this W naught, which induces a poleward flow. Okay, so it induces this poleward flow, the V component of the geostrophic velocity. So now we have this simple rectangle, which is our ocean, where we have a mass source, so the region where water sinks into the abyss, and that's the mass source for the abyssal ocean, so it would be this, okay? This would be S naught, water injected into the abyss. So we have some S naught, which is balanced by some uniform upwelling, this W naught. Okay, and if we have the sinking at high latitude, which is balanced by some upwelling throughout the basin, then this water must be circulating somewhere, and we say it's going to circulate in a western boundary current. We can do the same analysis as for the wind-driven gyre. You will get a western boundary current, and we will call this T west transport, T for transport. Okay. And the interior transport, which is given by this V at the surface, is going to be some T interior. Okay, so here I'm saying that the water sinks at the bottom, then circulates towards the equator, but not in the interior, but actually on a western boundary current. Then is upwelled uniformly with this strength, W naught, and then goes back towards the source region as an interior transport, which is this transport interior. Okay? So here is mass is injected to the abyss, circulates as a western boundary current, it is upwelled, and then in the upper layer there is an interior transport going back to the source region. So the conservation of mass says that you have an injection of mass, S naught. If you do mass conservation here between Y and Y naught, and this is Y south. Okay, if you do mass conservation in this region and you do a budget, in the bottom layer you have an injection of mass, S naught, plus you have injection of mass because of the interior transport, minus you're losing mass through the western transport, minus you're losing mass because of the upwelling. Okay? You add, well, this should be an X because it's going into, and then you have upwelling, which happens everywhere because it's uniform. Okay, so there is injection of mass into the bottom layer, and you get more mass through the interior transport, and then you're losing mass from the bottom layer to the upper layer through upwelling, and this transport of water out of the that box, the western transport. So this has to be equal to 0 in order to conserve mass. You have some injection of water, S naught. You have injection of water through transport interior, and you're losing mass because you're upwelling mass and you're transporting mass south of this latitude Y with this transport at the west. Okay? So you use again this that I didn't cancel. And so the poleward transport through the section at latitude Y, so the interior, T interior, is going to be X west from X east, you're integrating, V over H dx. So the total transport is the meridional velocity times the height, H. And so this is f over beta, w naught over h, dx. And so this is f over beta, w naught, x at the east minus x at the west. Okay, so this is the expression for my interior transport. The expression for the upwelling, so the upwelling happens everywhere, so I can do an area integral x west to x east, y, whatever that latitude is, until y naught of the upwelling strength, vertical velocity. Okay, so I integrate this upwelling throughout the area between x west, x east, y and y naught. And this is xe minus xy, y north minus y. Okay, so this is the expression for you. And so we are building a picture that looks like this. Okay, we're looking from the top here. You have an injection S naught north of y. Then you have a western transport taking the mass away. You have an interior transport, that arrow over there that you see is a meridional flow, but is also has also an eastward component. So we have this T at the west, and then you have the returning flow, which is the interior transport. And then you have upwelling everywhere. So now given these two, we can estimate the strength of the western transport. So T at the west has to be equal to S naught plus the interior transport minus the upwelling at latitude y. And this one as well. So the injection is equal to S naught. We still don't know how much that is. Plus the interior transport, which is this one, F over beta W naught x east minus x west, minus the upwelling strength, which is this, x e minus x w, y north minus y. So this is the transport at the west. Simply mass conservation. So in order to maintain mass balance over the entire basin, we know that the strength of the injection of mass is balanced by a uniform upwelling everywhere, right? So whatever mass you are injecting into the deeper layer is upwelled through diffusion uniformly. So S naught must be equal to the strength of the upwelling integrated over the whole domain delta x, delta y, because it's uniform. Okay? So you have localized source of injection of mass, which is upwelled everywhere from the bottom layer to the upper layer. So the western transport at that latitude y is equal to S naught, which is W naught delta x is, I'm going to use delta x, don't remember y, delta y, which is y north minus y south, because it's a global balance. So whatever you locally inject is uniformly upwelled, not just at latitude y. So S naught is delta x delta y, which is x e minus x west, y north minus y south. Plus this term, f over beta, W naught xe minus x west, which is delta x, minus W naught delta x again, y north minus y, not y south, okay? Because we're doing the mass balance here, north of y. So if you now rearrange this, you get W naught delta x y north minus W naught delta x y south plus f over beta W naught delta x minus W naught delta x y north plus W naught delta x y. So this goes with this. And if I didn't do any mistake, you get W naught delta x y minus y south, and then W naught delta x, so plus f over beta. And this is the strength of the Western transport. This, okay? So look at the picture. We have an injection of mass S naught localized, and that is balanced everywhere by upwelling. So we had that S naught was equal to the upwelling integrated over the whole basing. Then you have an interior transport, bringing mass back to north of that latitude y, and we have a return boundary transport to the west. So we had the expression for the injection, we had the expression for the interior transport, and now we have an expression for the western transport. Okay? And we are conserving mass. Now we said that this is our equator, so it's a one hemisphere simple rectangular ocean, so ys is at the equator. So we set ys to 0, and we're going to use the beta plane, so f if y naught plus beta y. And if we substitute with this, we get W naught delta x. Ys is equal to 0. So we have y minus f naught plus beta y over beta. And this is y naught delta x. Y minus, this is another y, so this is 2y plus f naught over beta.
Won't the y cancel?
Blah, 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 blah.
Yeah, it's plus.
It's a plus.
It's supposed to be plus y plus f naught.
It's a plus, yes. Okay, so now this is the expression for the western transport, setting ys to 0 at the equator and using the beta plane. If ys is at the equator, then F naught is equal to 0. So if naught is equal to 0, then this, so the Western transport at some latitude y is equal to, and using this expression over here, y naught is equal to s naught dx dy, but dy is s naught over dx y north minus y south, and y south is equal to 0. So this is s naught over dx y north 2y plus f naught, no, this is 0. So this is, why is the delta x going? Oh, because the delta x is there. So this is s naught 2y over y north. Okay? So that's the Western transport. As a function of y. So what is happening at the North Pole, we said that ys is equal to 0. Ys is equal to 0. And if we set this Western transport at the north, so yn, so the Western transport as a function of y at yn, the Western transport at y north is going to be equal to the injection. So this is telling me that if I have one injection of S naught, the amount of transport on the western boundary is going to be twice that injection. How can you have one injection of S naught and twice that injection leaving this area? Is because you have an interior transport, right? If you remember, the expression for the interior transport was something like f over beta w naught dx. This was the expression for the interior transport, which if you substitute with what we know is f over beta for w naught is s naught delta x y north delta x. This goes away with this. So you have, and you substitute f with f naught plus beta y, you get y naught s naught over y naught, which cancel. Okay. So the interior transport at y naught is equal to s naught. And so you have an injection of s naught plus the interior transport equal to s naught, and what leaves the area is twice s naught as a western transport, and then you conserve the mass. So the conclusions from this very simple box toy model, where you have localized injection of mass to the abyss, entering the abyss, then is uniformly upwelled. So S naught is equal delta x delta y vertical velocity. This generates a vertical velocity which balances the injection of mass S naught, and that generates an interior transport towards the north or the injection site. And at the same time you have a return boundary current on the west, this T W, which is twice the injection, because you have the injection plus the interior transport, and then you have twice the injection returning as a western boundary. So at the northern boundary, the equator transport in the western boundary current is equal to twice the strength of the source. The western boundary current is equator everywhere, and the northern mass flux at the northern boundary is equal to the strength of the source. So this is my T interior. Okay, you have injection S naught, which is upwelled everywhere, and you have an interior western transport. Okay, and that western transport is upwelled everywhere and returns as an interior transport, and that closes the loop. The fact that converges at the pole balances the western transport and the injection does not depend on the choices that we've made. This is just a simple toy model with a squared ocean. Okay. And this is the a better schematic than what I was trying to do on the blackboard. You have an injection site S naught that sinks to the bottom. That water that sinks to the bottom flows towards the equator as a western transport. And this westward transport starts as twice S naught, and it is slowly diffused and upwelled uniformly, goes back to the surface, and fills an interior transport that closes the mass towards the injection site. Okay? So this is the solution of the toy model. You have an injection site S naught. That mass flows as a deep western boundary current that starts as twice the injection S naught. As it is flowing, it is upwelled uniformly. So all these streamlines, they are slowly upwelled uniformly. And when they are upwelled to the surface, then they return as an interior transport towards the source. Then they did a laboratory experiment, which we could actually do in a rotating tank. So this is a sector ocean instead of a square basin. It's a sector ocean, okay, which is rotating. Has two layers. Surface layer, something like this, and a bottom layer. They inject a dye, some quantity, S naught, okay, which would be this. This dye falls and sinks to the bottom layer, and it starts spreading as a western boundary current at the bottom. You see this black here, right? As it spreads as a western boundary current at the bottom, it is upwelled uniformly, okay, and it starts filling and upwelling uniformly, and then eventually it will form an interior transport that will close the loop and go towards the injection site S naught. Yes? So the nice thing of this very, very simple model of the abyssal circulation, this is telling you when we were doing the simple thermocline with some warm water here and some cold water here, we were saying how thick is this thermocline, okay? And then we said there must be some convection here and some upwelling uniform throughout the thermocline to close the loop. And here you develop sinking motion, then through pressure gradients this is filling the whole basin, and then it is upwelled somehow through diffusion to the surface. Okay? This was a two-dimensional view of the system. Now with this very simple model we can have a three-dimensional view, and we know that this water that is going towards the equator is not doing so throughout the basin, but is actually doing it as a western boundary current at the bottom, which is that one. Okay? It's a western boundary at the bottom that flows in the abyss, and then it is slowly upwelled uniformly and is generating an interior transport, and this will be a western transport. Okay? And this is my uniform upwelling. and this is my injection site, S0. But now we know that the circulation is not two-dimensional. Okay, we know that the injection site then generates a western boundary at the bottom that is upwelled uniformly in this simple model, and then it's an interior transport. This is twice the injection, and this is as much as the mass injected into the system. So this very simple theory, or this very simple model, introduces the notion of a deep western boundary current. Okay, this western boundary transport is a deep western boundary current. And this is one of the few times, well, now we know, Einstein did it many times, so he developed a theory, and now we are developing through observations that he was right. But in this simple case of oceanography is a similar case in the sense that this simple model predicts a deep western boundary current before they observed it. Okay? They knew the Gulf Stream was existing because they could see the Gulf Stream, but they couldn't observe the deep western boundary current. So this model predicts a deep western boundary current, and actually then later they observed a deep western boundary current. So if you look in reality in the North Atlantic, you have the Gulf Stream flowing from the equator towards the north, and below the Gulf Stream there is a deep western boundary current flowing from the northern latitudes to the towards the equator, and that's the deep western boundary current predicted by this very simple model. Of course, again, as the wind-driven models, this is very, very simplified, and it's very wrong in many cases. For example, the widespread upwelling through diffusion, we know now that it's wrong, so that cannot explain the upwelling at the surface, okay? Because there is no widespread uniform diffusion upwelling the water. But at least the simple model predicts a deep western boundary current, which is actually observed. So you can go forward from, instead of looking at one simple hemisphere with the equator and one injection site, you can actually put more injection site and develop a more, well, I wouldn't say more realistic, but more complete view of the abyssal circulation. And so you get, this is another injection site at the close to the Southern Ocean, where you form that deep, very dense bottom cell. So if you put one injection site here and one injection site here, you have the injection site, the western boundary, deep current, and then upwelling, which is returned as an interior transport. And you can put another injection site here and get a more complete view of this Stommel-Arons model circulation, which predicts some of the features that exist in reality. Okay, but of course it misses a lot, because here the main assumption is that there is a uniform upwelling, which is not realistic. Okay. But at least it predicts a deep western boundary current, which is observed. Okay, an important assumption here is that of uniform upwelling, which is wrong, and a flat bottom, okay, which is again wrong. But some things are right, like through the Jostov vorticity balance, you get this upwelling that gives you a polar interior flow, which is right, and by mass conservation, a deep western boundary current, which is observed. The upwelling is a consequence of a finite diffusion, which in turn leads to deep convection, as in the model of sideways convection. In reality, the deep water might not upwell across all isopycnals at all, and in fact it doesn't, okay? But it moves along isopycnals and intersects the surface. So most of the water doesn't upwell through diffusion, but moves along the isopycnals and upwells in the Southern Ocean through mechanical force. In fact, through the presence of mechanical forcing, a deep circulation could be maintained even in the absence of diapycnal diffusivity. Okay, there were some experiments done where you actually turn off the diapycnal diffusivity, and for a sufficiently strong wind stress, you can upwell all the water back to the surface just with mechanical forcing, without any diffusivity. If you do the opposite, you turn off the wind stress and you maintain only diffusivity, you cannot upwell all the water with realistic vertical diffusivity. So the real circulation is qualitatively different from this very idealized Stommel-Arons model, but at least there is a deep western boundary current, which was not observed before, and with the simple model they predicted, and they were right. Okay, so this is the a general picture of a buoyancy-driven meridional returning circulation. You can think of convection, and you get convective cells, but we know that diffusivity is not enough, and it doesn't give you the right picture and the right strength of the circulation. And then these guys, Stommel and Arons, they try to understand what the abyssal circulation looks like. And so they said, okay, let's go back to this simple convective system. You have injection of mass, then you fill up the abyss, and then you diffuse all this water back to the surface. How does it work? And they, with this simple picture, they predicted a deep western boundary current, which is actually observed. Okay. But we know that this cannot be right because this vertical diffusivity cannot explain and cannot close the circulation in the cell. Okay. So next time we will see the role of the wind-driven circulation. Well, we will see the role of the wind stress in driving the meridional returning circulation.